Welcome to Calculus. Today we will investigate applying derivatives of polynomial functions, focusing on various ways that a derivative can appear in real-life contexts. Let's take a look at three examples. So our first example is a dive bomber. This dive bomber is flying from right to left along the graph of y equals x squared. When a rocket bomb is released, it follows a path that is approximately along the tangent line. Where should the pilot release the bomb if the target is at the coordinate 1, 0? So here we've got a function that really is a position function for a plane that's flying. So let's draw that picture to begin. So we'll draw a picture of this function y equals x squared. So recall from Algebra 1, that's our quadratic parent function. And it will have the graph of a parabola with its vertex at the origin. And that is the path of our plane, our dive bomber. So our dive bomber is somewhere along this path. We do have a direction that it's flying. So it's flying from the right to the left. So if I put some arrows there, that would indicate the path of the dive bomber. And somehow we want this dive bomber to release one of its rocket bombs so that it hits a target at the point 1, 0. So this point will mark here in green right on the x-axis, 1 out. And we're told that the rocket bomb should travel along a tangent line. So if we were to guess what that tangent line might look like, just to sketch it in, it might be something like this green line. And really what we're trying to answer is at what point along that curve, we'll mark it in blue, should the dive bomber release the bomb so that it travels along that green tangent line. So that's the point we're looking for. It's really that blue point right there in quadrant 1. And that, again, it gives us an idea about what to expect when we go to our calculations. So the first thing we should do is say, what is the slope of that tangent line? So recall that the slope of the tangent line will be given to us by the derivative of the function it's tangent to. So let's start off, if our function here is y equals x squared, the derivative of y is going to give us the slope of the tangent lines. So that's going to be this 2 carried down. So I'm just applying the simple power rule here. The old power of 2 comes down as a coefficient, x to the power of 2 minus 1. And that would simplify down to 2x. So then I want to see if I can write the equation for the tangent line and come up with some strategy using that equation that could get me back, get me back to this point, this blue point on the curve in the tangent. So I'm going to pick up the point slope form, and that is, again, y minus y1 equals the slope times x minus x1. So the things that I want to plug in are my expression for slope. So I don't actually have a number because I don't know where that tangent line is intersecting the purple parabola, but I do know that it's represented by the expression 2x. Again, that's this derivative of the original function. Recall that is representative of the slopes of all tangent lines given I know some x value. So I'm going to put that in for m. Let's fill in what other things we can. So I see that over here I've got a point, 1, 0. So that I could fill in for x1, y1, because that point needs to be on the tangent line if the rocket bomb is going to hit its target. So I'm going to plug in that 0.10. So x1 is 1. So x minus 1. And I can also plug in the y there, which is 0. So I'll do that on this other side. So it's y minus 0. And that I need to simplify. So I'm going to reduce that left side. Y minus 0 is just y equals, and then I've got 2x times x minus 1. I'll distribute the 2x through, and that gives me 2x squared minus 2x. So it doesn't look like much of a line equation right now. It looks like a quadratic. But again, what I'm really going after is what's the x value of this blue point. So one thing that I can do here is just note that I do know what y equals here at that intersection of the tangent and the original curve. It equals x squared. So I'm going to make a substitution of x squared for y from my original function. So that equals 2x squared minus 2x. So this equation I want to solve, and I want to get an x value that will tell me where is the, and really it's considering this as a system of equations, where is the x value for this intersection of the tangent line and the parabola. So to solve there, I'm going to subtract x squared from both sides. That'll cancel on the left. And that'll give me this equation, 0 equals 1x squared, or just x squared minus 2x. So now notice my substitution, treating this like a system of equations, has reduced this down to just the x variable. So I can solve that equation now by factoring. So I'm going to factor out an x, and that leaves the binomial x minus 2. And there's two potential solutions here. Could be that x itself is 0. It could also be that x is, if I set x minus 2 equal to 0, add 2 to both sides, x equals 2. Now let's consider both of those potential solutions. So what I need to consider is that could be the x value of the intersection of the original function and the green tangent line. So if I look at, first of all, the 2, because that's kind of the one that I see here. Here's x equals 2. And for me to find the y value for that, I really just need to plug it into the original function, since I'm looking for the intersection of the original function with the green tangent line. So we'll plug in 2 for x. So I'm trying to write the coordinate. It's 2 comma, and then I'm going to plug in 2 here for x, 2 squared. And that gives me this potential spot of 2 comma 4. Well, one thing we can do is we can check it to see if that actually fulfills these restrictions that this question's presenting us. So first thing is, I could say, let's rewrite the point slope formula to actually give us the equation of a line. So I'm going to take and rewrite this point slope. So y minus, and at this point I could use either 1, 0 or 2, 4 for my x1, y1. So I'll use 1, 0 because I know that has to be on the line. So it's y minus y1 is 0 equals, now the slope of the line, I could find that in various ways. If my x value is 2, I know from my derivative that the slope should be 2x. So that line should have a slope of 2 times 2, or 4. And then x minus x1 is 1. So this could be my potential equation, y equals 4x minus 4, if I distribute that through. So let's do this. Let's look at that as a potential tangent line that could contain the points 1, 0, and 2, 4, and see if that actually intersects the quadratic. Let's go to Desmos just to check here. So I'll type in y equals x squared. There's the original function, the path of that flight dive bomber, and then y equals 4x minus 4. So we're checking two things. Does it intersect the parabola here at 2, 4? And that looks pretty good. That visually inspects very well. If I zoom in, I can see that that is in fact a good tangent line right where that blue line's intersecting my red curve at 2, 4. I can also see that that goes through the x-axis there at 1, 0. So that all checks out. Let's head back to our notes screen here. Let me make sure to show the Desmos view. I may have just been showing the notes. So again, I've got my function here in red. That's the parabola. And then I've typed in that equation y equals 4x minus 4. And again, the 2 points I was checking here is 2, 4. That's really our answer. And also this location that we're trying to strike with the bomb at 1, 0. Well, let's go back and finalize that answer. So we'd come up with this point 2, 4. And really that could be the location of this plane right there in quadrant 1 as the plane's flying from right to left. So here our first application of the derivative is really a position function, and the way we're using the derivative is finding the slope of a potential tangent line. Let's take a look at an example where we are looking for a rate of change. Our second example here is about water that's leaking out of a swimming pool. So the swimming pool measures 20 feet by 40 feet by 6 feet. The amount of water in the pool at a time t is W at t equals 35,000 minus 20t squared gallons, where t equals the number of hours since the pool was last filled. At what rate is the water leaking when t equals 2 hours? So really, we just need a couple things here to find this rate. The first thing we need to just recognize is that the amount of water in the pool is given by this function W of t equals 35,000 minus 20t squared. So just looking at that function, we can see that the maximum amount of water in that pool is going to be 35,000. And that's when the time is 0. Everything past time 0 is going to subtract from that 35,000. So the way the function is written is with the idea in mind that the water is somehow escaping the pool. It's leaking out of the pool. So the way that we would find the rate at which it's leaking is really to apply the idea of a derivative. So I'm going to take the derivative of this water function. So we'll put our notation here, w prime of t, or the derivative of w of t. And so I'm just going to apply some of my polynomial derivative rules. For a constant, remember the derivative of a constant like 35,000 is going to be 0. And then I'm going to apply the difference of two functions derivative rule. So we're going to take a derivative of negative 20t squared separate from the 35,000. So that's going to be the constant 20. Constant multiplier just sets out front. And then I'm going to apply the simple power rule to this t squared. So the old power 2 comes down as a coefficient. And then it's t to the power of t2 minus 1. And I want to just simplify that expression because it looks complicated now, but really it's reducing down to simply negative 20 times 2. So that's negative 40. t to the power of 1. And that would represent the rate that the water leaks from the pool. We can interpret that negative sign. Negative sign there really means water is leaving, so we're losing gallons. So when I look at the question, it's saying at what rate is the water leaking when t equals 2 hours? So what I really need to calculate is not just the derivative of the function, but the derivative of the function when time is 2 hours. And that's pretty straightforward to apply. I'm going to take my derivative negative 40t, substitute in 2 for t, and that very handily gives me this rate of negative 80. And if I put units, it would be gallons, since that's the volume of the water per hour. The time period here is an hour. We're losing 80 gallons every hour. So if our first situation was really using the derivative as the slope of a tangent line for some dive bomber trying to hit a target, in the second example, we're using the derivative in a way to find a rate of change from an original volume function. Let's take a look at another example where we are looking at the derivative in terms of rate of change. So this scenario has to do with the velocity v of a liquid flowing through a cylindrical tube. It's given by the Hagen-Poiseuille equation. Velocity equals k times quantity large R squared. They'll tell us in a moment, large R is the radius of the tube, minus little r squared. And I see here that little r is the variable distance of the liquid from the center of the tube. We're also told that k is a constant that depends on the length of the tube and the velocity of the liquid at its end. So that's a predetermined constant. We can just treat it as such. So as I look at this equation, what I really need to decide is what's going to change, what's always going to be the same. So really, the only two things that are going to change is the velocity. So I'll put that in red. The k constant, by its very definition, doesn't change. It's a constant. The large R radius of the tube will not change. So it also, we're going to assume that's going to be just a number that we're dealing with. What will change is this small r. We can kind of see it here, the word variable. So it's something that changes based on the distance of the liquid from the center of the tube. So when we look at the equation kind of from the perspective of what's changing, what's not changing, it's just these two variables, the velocity, and it is a function of the distance of the liquid from the center of the tube. So let's it's always helpful to draw some type of illustration. So here's a tube filled with liquid. And I believe that this equation applies to arteries in the human body, so blood vessels. So what we're saying that this small r is, and we'll write it in red here, is that it's, for instance, if I've got a stream of liquid, if somehow I could isolate it there, and that blue point is the center, the little r is the distance from my fluid to the center. And so you can see why that'll change. There's a lot of different places that I could be tracking a fluid moving through a tube. And definitely they're moving at different velocities. So the original function is just velocity. So when I go to part A, which is my first question, find the rate of change of the velocity with respect to r at the center of the tube. Really, this is like a physics consideration where I'm looking at something like acceleration, but I don't need to think too much about that, because really all I need to identify is that I'm looking for a rate of change of v with respect to small r. What's that mean for us? I just need to find the derivative of this equation. So I'm going to take the derivative of the velocity equation. To help me out with this, I want to distribute this k. So I'm just going to send it to each of those terms. And this will be kr squared. So that whole product there, k big R squared, that's a constant. Minus k little r squared, that's a polynomial. So it's got a variable squared with a constant coefficient out front. So I'm going to work on this version as I write the derivative. So the derivative of a constant by my derivative rules is 0. And then the derivative of a polynomial with a constant coefficient out front is going to be minus k. And then the derivative of r squared is going to be 2. The old power becomes a coefficient times r to the power of 2 minus 1. So I want to simplify that. That becomes negative 2k r. And that is my rate of change of the velocity with respect to the distance of a stream of liquid somewhere in the tube to the center of the tube. What's the distance between that location and the center? So that's in general for any placement of fluid within that tube. Part B is specifying now. It's saying, okay, so what's the rate of change halfway from the center to the wall of the tube? So we just need to think for a moment how I could represent that within my derivative function here. So I want to substitute something in. So it's going to be a substitution of a value here. And I'm going to pick up this derivative we just wrote, so negative 2k. But I'm not going to write small r because I want to plug something in there that would represent half the distance from the center to the wall of the tube. So we just need to go back to the original equation. We were told that big R is the radius of the tube. So if I've got this whole radius is big R, half of that would be half times big R. And that's what I want to substitute into my derivative. Half times big R. Remember, big R is a fixed number. It is the radius of the tube. Well, I just need to simplify that once I've substituted it. So my 2 and my half are going to cancel each other out. So this is going to be negative k times the radius of the tube. And that is the rate of change halfway from the center to the wall of the tube. The last question is, what's the rate of change at the wall of the tube? So here again, I'm going to use that same derivative, and I just again want to substitute in some value that would represent the distance from the center to the wall. So again, I kind of have that written already. That is big R. By definition, the distance from the center to the wall is going to be the radius. So here I don't need to put any fractional multiplier, it's just R itself. And as I substitute that in, we solve directly. That's negative 2k big R. So definitely we can see a variety of ways that we can apply derivatives to real life scenarios. We've seen one example where we had a dive bomber and we were using the derivative to decide about the slope of the tangent line. And then we've seen two examples about rates of change given original functions that provide measurements for different physical phenomena. In one instance, we were watching water escaping from a pool. And on this third example, considering liquid moving through a vessel. through a cylindrical tube. So although we have kind of a single concept for derivative, its applications are manifold. Well, thank you for joining for this investigation. I'm going to let you apply your derivatives to your real life scenarios. See you soon.